we continue our investigation about integration and continue expanding this idea of substitution, let's just remember where we've been, is that we've been using the idea of integrating u to powers. That is, we looked for an integral inside the integral where we had something to a power, and then that made us guess what we were going to do for our u value. So we were trying to get into this form, the integral of u to the n with respect to u. Now, we know of some other forms, and so let's talk about what would happen if we had the integral of e to the u with respect to u. See, of course, we usually talk about the integral of e to the x with respect to x, but it really doesn't matter what variable we're referring to. The integral of e to the u with respect to u would just be e to the u plus a constant integration. So what we're going to be facing ourselves with is we're going to be having integrals, for instance. What example number are we at now? I think example number 9. So, for instance, example number 9. We're asked to find the integral of, say, e to the 3x with respect to x. That's what we're supposed to find. And the thing that we need to recognize is that we can't just say that's e to the 3x power, because the rule, remember, is that the main rule that we're going off of is it's the integral of e to the x with respect to x is e to the x plus a constant integration. It didn't tell us about what happens when we have a power other than x. Okay, so, or a power other than u with respect to u. So what we're really needing to do is we're needing to end up with a e to the u power to do this integral. And so that kind of gives us the hint, a very strong hint, that we're going to replace the power, which is 3x, with a u. So our integral is going to look like then the integral of e to the u with respect to x. And now we're back to the same idea we've seen previously. We need everything to be about u. We can't have any x's in there, so we have to do something about that dx. Well, if u is 3x, then du is the derivative of 3x, which is 3 times dx. And so now we have before us a way to replace the dx in our integral. See, we need to replace this dx, and we have a dx here that we can solve for. So we'll multiply both sides by 1/3, and we'll get our dx value. It's 1/3 du. So we can now say we are looking at the integral of e to the u times 1/3 du. Now that 1/3 being a constant factor, and it's constant. We can't pull a variable out, but that constant we can pull out, and now you see that we have something very simple to integrate. The integral of e to the u with respect to u, of course, is just e to the u plus our constant of integration. And then we understand that the result we would get there, I mean, that u is really 3 to the x power, isn't it? Plus our constant integration. So there's the correct result, correct answer. Now, just as a reminder, we could check this, and the way we would check it is that we would find the derivative of our answer with respect to x. We'd find this derivative, and we better get e to the 3x. We better get what we started with. Well, how do we find the derivative of a sum? Well, certainly it's the derivative of the first term plus the derivative of the second term, but the second term is just a constant, isn't it? And so the derivative of constant is 0, so we're kind of not too worried about that. And now the derivative of 1/3 e to the 3x, well, that's 1/3 times the derivative of e to the 3x. And if you remember how we took derivatives of e to powers, then what would we do? We'd say, okay, it's e to exactly the same power, but we had to use the chain rule, which would tell us we also have to multiply that with the derivative of the power. And so we'd have to say times the derivative of 3x. Well, of course, that gives us a 1/3 times e to the 3x, and the derivative of 3x is just 3. And you see now that we have a 1/3 times a 3, which ends up being 1, and so we're left with just e to the 3x. And so it does check out to be correct, doesn't it? Okay, let's take another look at another example here on the next page. Okay, in this problem, we're asked to find the integral of x squared e to the power 4x cubed plus 1 with respect to x. From what we just discussed, when we have these powers of e, we really want to get it turned into, see, again, we're going to try for having this form, integral of e to the u with respect to u. That's our game plan. And so if that's going to be our game plan, we immediately recognize that we need to make the exponent our u value. Now, we can kind of decide, as we discussed this before, we kind of can decide here, that's what it would look like at this point, wouldn't we? We can decide whether this is a reasonable substitution, because if we imagine the derivative of this u, we're going to get 12x squared, aren't we? And we have the x squared kind of as an extra part right there, and we know that that will be necessary. If we had an x to the 4th there, or if we had an x there, we would have more trouble. We would have a lot of problems then. We really need an x squared because du is going to create an x squared. See, so that's why we need that x squared to be able to replace x squared dx. Anyway, here's the information we have. We will next, so I replaced our exponent with a u. And then, as we've done before, we probably want to rearrange things just so we can see it all in a nice, neat bundle there. And so it's the x squared dx that we're concerned about replacing now. And here, with our du, we see an x squared dx. So we recognize that 1/12 du is actually that x squared dx. So we can come in here now and we can replace x squared dx with a 1/12 du. We recognize, we might do this all in one step, we recognize that 1/12 can come out, and now we just have the integral of e to the u with respect to u. And so now it ends up being pretty easy, doesn't it? We have 1/12 times e to the u plus a constant integration. The integral of e to the u is e to the u. And so that power of u really is the complicated power 4x cubed plus 1 and plus our constant integration. And we can check this as we did a moment ago, and we'd find that we're correct. Now let's do one more example with e to a power. And this is one that we just have to be careful of, because if we get in a hurry and don't work at it, we think we can do it real quickly. And it takes a bit of work, not very much. Find the integral of e to the negative x with respect to x. Okay, actually maybe a couple more. E to the negative x with respect to x. And what I would remind you of is we can integrate e to the u with respect to u, we can integrate e to the x with respect to x, but we don't have a way directly of integrating anything that's other than just an x or just a u or just whatever the variable is. And so if we go about our business as we have in the past, we want to replace that exponent with a u. Now in that case, du would be the derivative of negative x, which is -1 dx. Okay, so when we come in here to do our replacement to find our integral, see, when we do this replacement, we'd say, okay, well now e to the negative x, the integral of e to the negative x with respect to x is the same as the integral of u with respect to x. But what we need to do is multiply both sides by -1, because we're needing to replace du, aren't we? So -1 times -1 is positive. So I said replace du. We're really needing to replace dx. And now we have a replacement for that dx. It's negative du. So this is the integral of e to the u times our negative 1 times our du. We'll bring the negative 1 out and just integrate e to the u with respect to u. And of course, then that ends up being negative 1 times e to the u plus our constant of integration. But we see that that's just the negative of e to the negative x plus our constant of integration. I said just one more, but I tell you what, I want to throw one more thing out here. I don't know if we'll go all the way through it because I'm about out of room. But another one would be something that might look like the integral of e to the power x over 2. See, we might be faced with something that looks like that. And it's not going to be a big problem, but if we think about this correctly, and that is, remember, we want our exponent to be u. That's what we want. So we would integrate this and would say, we would substitute and would say, this is e to the u dx. So we've got to get rid of the dx. Now, it's a little more difficult here to get rid of the dx if we think about it as x over 2. But it's easier to do this if we think about u as being 1/2 times x. Isn't that what x over 2 is? And then du is just the derivative of 1/2 x times dx. And of course, the derivative of 1/2 x is just 1/2. So that ends up being 1/2 dx. Now, we need to we need to solve for dx. And so to do that, we'll multiply on both sides, not by 1/2, but by 2. Because when we multiply 1/2 by a 2, we get a dx, don't we? We just get 1, So now when we do this substitution, see, we're going to replace dx with 2 du. And so that 2 is going to come to the outside, and we'll just have 2 times the integral of e to the u. And of course, integral of e to the u is e to the u, but u is x over 2. So this is 2 times e to the power x over 2 plus our constant of integration. So just a little twist. Here's what I was wanting you to be concerned about, how we write x over 2 in a form that makes it easier for us to find du. Okay, well, we're going to go to another type of example on the next page. So let's go to the next page. Okay, look at example 13, and we're to find the integral of 1 over 3x plus 5 with respect to x. Now, of course, we've got that form up above, but before we talk about that, let's, I kind of gave a hint of what we're going to do here before we even get started. The first examples we looked at, we had an expression in parentheses with a power on the outside, and so it was what was in the parentheses. We were looking to get u to a power, so it's what was in the parentheses we made u. And if we had radicals, square roots or cube roots, then it was what was underneath the radical that we made u, because we knew that that could be u to a fractional power. And then if we had a denominator where we had something to a big power, parentheses in the denominator with a power on that, then we would recognize that that would give us a situation where we really had a negative exponent on u if we made u was what was inside the parentheses. And then we just got finished looking at what happens if we have integral of e to powers other than x. Well, then we would substitute u for the power. And so we kind of have this thought of how we might attack these problems in the future. Now, in this example 13, we don't have anything, we don't have an e to a power, and we don't have parentheses with a power on it. We just have a plain old denominator. And so what I'm wanting you to remember is that we do have this other special integral. Now, we talked about it being the integral of 1 over x with respect to x is natural log of absolute value of x. But we're going to try to get it into the form of 1 over u with respect to u. And then that we can do that integral as a natural log of an absolute value. So if we compare the form we're trying to get, see, we're going to be trying for the integral of 1 over u with respect to u. So there's no powers on u except 1. And if we can get that, then we can do the integral in this way. And so that would lead us immediately, I think, with that big hint, that we're going to replace this whole denominator with u. We're going to let u be 3x plus 5. So our integral ends up being the integral of 1 over u, except it's dx. See, that's the holdup. That's the issue. We've got the 1 over u business, but now we've got to deal with the dx. So we go back to our definition of u, and remember, du will be the derivative of u, which is 3, times dx. So we need to replace dx, so we've got to solve for dx, and we do that by multiplying both sides by 1/3. So now we end up with the integral of 1 over u, and instead of dx, we have a 1/3 du. Now, as always, we're going to factor that 1/3 to the outside. So now we have 1/3 times the integral of 1 over u du. And now we can do the integral of 1 over u. We have our 1/3. The integral of 1 over u is natural log of absolute value of u plus our constant. And then we resubstitute. We put back in our u value, which is 3x plus 5. So it ends up being 1/3 times the natural log of the absolute value of 3x plus 5 plus our constant of integration. Now, we need maybe to look at another 1 or 2 examples here, and then we'll be done. Okay, our next example, we're to find the integral of 2x divided by x squared plus 1 with respect to x. And this form is probably the easiest one to overlook, because we're looking for radicals, we're looking for e to powers, we're looking for parentheses that have powers on them, and we don't see any of that here. And so it's kind of our last line of defense is that, well, we need to think about this 1 over u business. And so if we were going to think about having this in the form of 1 over u, the integral of 1 over u, that would mean that the u would have to be the x squared plus 1, because that's the only way we would get u in the denominator. Now see, the denominator doesn't have a power on it, but if we did that substitution, then this integral would look like the integral of 2x over u with respect to x. That's the way it would look. Now, when we consider this, then we need to replace the 2x dx business. And here's what I'm getting at. This 2x over u, we've seen this idea before. We could write that as a 1 over u times 2x. Isn't that 2x over u? And then we still have this dx out here. So what we're needing to do is to get rid of the 2x dx. Now, clearly we could factor the 2 out. But if we're observant, if we think about this in enough ahead of time, we notice that du is 2x dx altogether. So we're kind of lucky here that we don't really need to factor that 2 out. We get exactly our du over here. That's exactly du. So this ends up being the integral of 1 over u du. And then, oh, this one is actually easier than the first one, if we knew what to try. So this is the natural log of absolute value of u plus our constant of integration. And then we don't forget we need to replace u with x squared plus 1. Now, here's something else. I could say that's the answer, but if you were to look this answer up, that's not the answer you would see. Now, it's a correct answer, but it's not the answer you would see. Once in a while, you're going to see absolute values disappear completely. See, and you'll think, well, why doesn't my answer, the answer they're showing me, why doesn't it have absolute values in it like mine does? Well, here's the reason. X squared plus 1, imagine anytime we put a value in for x and we square it, we get positive, or the worst we could get is 0. You know, x squared is either going to be 0 or positive, isn't it? And then when we add 1, then we're going to get 1 or some positive number bigger than 1. So we're going to have the absolute value of a positive number. The x squared plus 1 is always positive. That's what I'm getting at. So the absolute value of x squared plus 1 then is just x squared plus 1, because we're taking the absolute value of a positive number. So in this case, we don't really need the absolute values, and so we would see it written as just the natural log of x squared plus 1. Okay, one last problem to do on the next page. Okay, we're to find the integral of the fraction x plus 3 over x squared plus 6x with respect to x. And again, we're in a position that we don't see parentheses with a power anywhere, and we don't see any radicals, so we don't know how to choose u in that fashion, and we don't see e to a power, so we just see a fraction. And the only tool we have so far, again, is trying for the form integral of 1 over u with respect to u. See, that's about the only thing. If we had some parentheses with powers or radicals or e to powers, then we would have a better guess. But this kind of leads me to believe that we're going to make a substitution, and we're going to actually make the entire denominator our u value. And so if we do, that will create a u in the denominator, won't it? So, and then what that tells us then, okay, that this integral of the fraction x plus 3 over x squared plus 6x with respect to x, we can convert into the integral of x plus 3 just over u with respect to x. Now that still looks foreign, but we've seen this idea before that we can think of the fraction x plus 3 over u as 1 over u times the numerator x plus 3. So it ends up being the x plus 3 that we're trying to replace now. Well, how do we make a decision to do that? We look at our original u value here, don't we? And from it, we decide what du has to be. Well, du is the derivative of u times dx. And in this case, the derivative is 2x plus 6. So it's a little more complicated du in the past. And that doesn't look like what we have down here. We have an x plus 3 times dx. And now, we have to have enough algebra under our belt to recognize there's some similarity with this x plus 3 and this 2x plus 6. And that is that 2x plus 6 has a common factor of 2, and when we factor it out, we actually have an x plus 3, don't we? So we're able to solve for this x plus 3 by multiplying both sides by 1/2. So whenever we see an x plus 3 dx, we can replace it with a 1/2 du. Now, I'm going to do this one a little bit differently than I have before, because I know I'm going to put a 1/2 du right here, aren't I? And I know that that 1/2 I'm going to end up factoring out, so I'm just going to do it right now. I'm going to put that 1/2 for the 1/2 du is going to be, and then I'm just going to put my du down. So I took that 1/2 out all in one step. Now I've got 1/2, the integral of natural log of 1 over u is natural log of absolute value of u. And in this case, the u is actually x squared plus 6x. Now be careful. Here the absolute value is necessary. So for instance, if x was -2, we'd end up with a 4 minus 12 there, see, which would be negative. It was only in that case similar to what we saw in example 14, where sometimes the absolute values can go away. In this case, it can't. So this is our final answer. And this is the last of my examples for this substitution technique of integration. I hope it's been useful. I know it's been long.